A2 Further Maths, Roots of Unity. Right, so given the square root of 3 plus 2i equals a plus bi, can you find the values of a and b for me, please? So using your year 1 skills, just see if you remember how to go about finding the a and the b value when you square root a complex number. Okay, so you might want to pause it there, have a go yourselves, and then carry on when you're ready. Okay, so let's see how far you got. Hopefully you realise that you need to get rid of that square root by squaring both sides first of all. Then once you squared both sides, you can expand this side to get a squared plus 2abi minus b squared, because you're going to get an I squared in there. And at this stage, what you can do is you can equate the reals and equate the imaginary parts. So we've got the 3, which is real on that side, must be equal to a squared minus b squared. And we've also got 2i is equal to 2abi, so therefore we've got 2 equals 2ab. Now we can make use of both of these, maybe rearranging this one and substituting it in there will be the easiest option, and then we can work out both the a and the b. So I'm rearranging this to get 1 over a equals b, and then from there I can substitute that into this part. There we go. We can expand and multiply through by a squared, which gets rid of that denominator, and then I've got a hidden quadratic here with a squared number, so therefore I could use the quadratic formula to work out what a squared is, and then once I know what a squared is, I can then go on and work out the two values of a. Of course, I can ignore the negative. All right, notice I've just done the positive version there. I can ignore the negative because if I square rooted, then I would end up with an imaginary number, but both a and b are real numbers. That would be written there in an exam question. Find the values of a and b given a and b are real. Then once you've done that part, then we're going to get, we know what a equals, square root of 3.303. So a equals roughly 1.817, and that would lead on to b, because we can use this part just here to get b equaling 0.550. There's nothing to three decimal places. There's nothing new about this. This is the work you did in your first year, so there's absolutely nothing new at all. Of course, just writing the end answer out is a good idea. The other solution, of course, is when you square rooted, although here it couldn't equal a minus. Once you square root it, the a value can equal 2 values, and then because the a value can equal 2 values, that b value can equal 2 values as well, and there's the other one. And of course, you can easily type this in your calculator. You can square it, and hopefully your answer will be 3 plus 2i. Okay, grab your notebooks then, please. Let's move on to the same question, but this time looking at it with exponential form. So I know that 3 plus 2i can be written as a plus bi, but I also know that a plus bi can be written in exponential form, re to the I theta. So what I'm going to do is I'm going to see if I can find the values of r and theta using that. Now, the first thing we do is exactly the same as what we did in the previous example. We can say because we got the square root equals re to the I theta, I could square both sides. And if I square both sides, I can see that I've got 3 plus 2i equals re to the I theta squared. Now, because that's squared, and my laws of indices say I can put these two together, I know that I can write that as e to the 2 theta. Now, if I can work out this part in re to the I theta form, then I could do some comparing. So that's exactly what I'm going to do. I'm changing the 3 plus 2i to r and theta form. So just to make sure you're aware of where these two come from, I've got 2 squared, 3 squared, square rooted. Square root 13 comes from, and the 0.588 comes from me doing tan to the minus 1 of 2 over 3. So then I've got my value, and I also know that theta is between 0 and 2 pi. That's the range of values I'm looking for this theta. So that is as far as I've got so far. But what can I do now is exactly the same as the previous one. I can compare the two parts. So I put them together. So there's my 3 plus 2i. I know that's the same as just here, 3 plus 2i, which is exactly the same as r squared equals ei2 theta. So because those two things are the same, I can now compare coefficients. So I can compare the fronts and I can compare the coefficients of I. So I get two answers. I get root 13 equals r squared. So therefore I get r equals roughly 1.9. I then have got 0.588, which is that number just there, is equal to the 2 theta. But I know that if I've got the values of 2 theta, because theta was between 0 and 2 pi, 2 theta is going to be between 0 and 4 pi. Now that's important because it means you're going to get more than one possible answer that when you square root it, takes you back into the 0 to 2 pi region. So what does that mean then? Well, the first answer is just a graphical representation. So there you go, 0.588 is your first answer for theta. But your other answer could be, because it's between 0 and 2 pi, all the way round to the other part. So to get the 2 pi, all I need to do is add 2 pi. 6.871 as your theta value is exactly the same as 0.588. All you've done with 6.871 is gone all the way round to get 2 pi, which is just a bit over 6, plus this extra bit of 0.588, which is where you've got that from. Now, both of those answers are exactly the same. And when you square root it, that's why you're going to get that going back to this sort of answer just here. So I know that 2 theta equals 0.588 or 6.871. And in that case, I also know what theta is going to be, 0.294 and 3.44. Noticing that our theta values are both within our original range. And that's important because that means that you're going to get two possible solutions. If you miss this bit out, you'd miss out one of your solutions. So then what? Well, therefore, the square root of that equals 1.90 e to the 0.294i or 1.9 e to the 3.44i. There's our two solutions. And there's no surprises that both of these, if you actually work them out, 1.9 cos of 0.294 and 1.9 sine of 0.294, you're going to get exactly the same answers as in the previous one. All right, you can check that on your calculator. So both answers ended up being exactly the same, as you'd expect. You might be thinking, why do it on exponential form? Because when you get to harder ones like this sort of thing here, it's a lot harder to find all the solutions. Now, this one isn't so bad, because it's just a simple z to the 4. But when it starts getting more complicated, then you will need to know how to do it with the exponential form. Right, so what I'd like you to do then, please, is find the solutions. It says there, find the solutions to z to the 4 equals 16. Okay, so you might want to pause it, make sure you got your answers, however you want to word it. Right, let's see how far you would have got then. So the obvious answer that you should have got is 2. 2 to the 16 is 2 to the 4 is definitely going to be 16. And you might have thought, oh, I'm not going to get tricked out. I also know minus 2 to the 4 is going to be 16. But what you might have missed is the fact that you've also got 2i. Because we know that I to the power 4 goes back to 1, 2i to the power 4 is going to get you exactly the same answer. So only get you 16. 2 to the power 4 is 16. I to the power 4 is 1. So 16 times 1, 16. And also, by that same rationale, you could have minus 2i. So those are your 4 possible solutions. Just be aware that whenever you're dealing with a power like this, z to the 4, if you're dealing with the complex numbers, then you're always going to have n possible solutions. They might all be real, you might have some complex ones in there, but you'd always get 4 possible answers. As you know from normal maths, if you had x to the power 4 equals 16, you only deal with these two, and you often have written no real solutions apart from those two. And that's because they ignore the complex answers. Okay, so let's have a look at this question then. So I've got an opportunity to write it down in your notebook. Have a think about it. Given z to the 4 equals 2 minus 4i, find all the possible values of that complex number in the form a plus bi. Okay, so I'll pause. There we go. Okay, so you might not have started it yourself. You might want to work through this one together. So the most important part to notice is that you can do it the same as before by expanding it and comparing coefficients, but you're going to be there for quite a while. It's going to get quite complicated because you're dealing with the power of 4. So it's a better idea to use the exponential approach. So the first thing I'm going to do is think about writing z as z to the power of 4. So I know that z equals re to the I theta. Okay, even though it's saying write it in this form at the end, I know that a complex number can be written in exponential form like that. So that's where I'm going to start. Once I know it's written in exponential form like that, what I can do then is I can say, well, z to the 4 is going to equal rei to theta to the power of 4, which is exactly the same as r to the 4 e to the I 4 theta. Okay, right. Now I know that that is z to the 4, so I also know that that is going to be equal to 2 minus 4i. So I can write 2 minus 4i in exponential form by finding the modulus, there we go, and the argument. So once I've done that, root 20 e to the 5.716i. That is what 2 minus 4i looks like. So there's z to the 4. There is 2 minus 4i. And what I know is that those two things are going to be equal to each other. Important to make sure our theta value is between that. Come back to that in a second. So therefore, I can now write this answer. Why does that help? Because now I can start to figure out what the r value is and what the theta value is. So the r value is r to the power 4 is root 20. So therefore, you can do the fourth root of root 20 and the r value comes out to be 1.454. The theta value, I need to be very careful. 5.176 is equal to 4 theta. So therefore, I've got one answer which I definitely know, okay, which is just going to be 5.176. But the other answers I get, I just keep adding on 2 theta. I keep going round and round to the same answer. And because I've got 4 theta, because I've got to the power 4, I should have 4 possible answers. So I'll just keep adding 2 pi to it till I get all 4 answers. And there we go. Right, once I know what 4 theta is, of course, then I can work out what theta is. So there we go. Noticing that then all of these answers here take us back within 0 to 2 pi. Okay, just before I got to 2 pi, but they're definitely all 4 of them are in there. Right, so this is pretty much done now. I've got my theta values. I've got my r value just there. All I need to do now is write out my answers. So the first answer I'm going to get is going to be 1.454. Each of them have got the same number at the front. E to the I theta, where the theta values are those 4. So there are my 4 solutions. The answers at the end want to be in a plus bi form. So all I need to do is just go through 1.454 cos 1.294 plus 1.454 sine 1.294 I. So that's where these answers are going to come from. Okay, noticing that they are very similar. Usually they're just a bit of variation with the negatives and positive signs. Okay, so pause there if you need to. Right, given that z to the 5 equals 1.5i, find all the possible values of z. Right, so that's the same as the previous question. I'll give you an opportunity to do that yourself. So pause there, have a go, find all the different solutions. Okay, so let's see if you've got these same solutions as I did. So I got r to the power 5 equals root 26. So therefore r is equal to 1.385. I also got 5 theta is going to be 1.373. I keep adding 2 pi on until I've got 5 different solutions. There we go. And then I can get my theta values from there, noticing that all of these are between 0 and 2 pi. Fantastic. So therefore, I've got all my solutions then. I just need to put these together and write out the answers. There we go. So there's my 5 roots of this equation just here, the 5 solutions for this equation. And don't forget, you could check any of these. If you type that in your calculator to the power 5, it should tell you this answer or the exponential version of it. Right, all I've done then is write it in terms of a plus bi, so there we go. And there's our 5 different roots. What I'd like you to do is this, is just plot each of those points on an Argand diagram. Okay, so pause there, sketch your Argand diagram, plot each of those points. See what you notice. Okay, so hopefully you've plotted Z1, 1.33 across, 0.376 up, roughly goes about there. Z2, 0.05, so very close to this line, 1.38, it goes about there, and so on. Okay, Z3, Z4, and Z5. If you join those points up, then what you'll notice is they form a polygon, in this case a pentagon. And what's important about it is a regular pentagon. They are the 5 vertices of a regular pentagon. There's no surprises it's a pentagon because you were dealing with z to the power 5. You had five answers. But what's important is it is a regular pentagon, all with an equal distance from the origin, all perfectly spaced out. I'm just going to round each of those answers to 2 decimal places. So same answers, just rounded to 2 decimal places. What I'd like you to do, just add all those together. Okay, so grab your calculators, add them all together, see what you notice. Okay, when you've done that, carry on. Okay, so hopefully when you typed them all in and pressed equals, there was no surprises to the fact that you got exactly 0. In fact, when you add up all the roots of any of these equations, it always equals 0, and I'll prove that to you later. Okay, for now, it's just an important fact that you can just take from that one example. The sum of the roots is always equal to 0. Okay, grab your notebooks for me then, please. Just take these 2 notes down. So when you solve any equation in the form z to the power n equals a plus bi, so any power, these 2 facts, this is how you're going to go about doing it. So it's almost like an algorithm, a list of rules on how you find the solutions. So you write z in exponential form using de Moivre's to get that. So that's the first thing you should do. So you're rewriting it using de Moivre's theorem. It's de Moivre's theorem because you've got n theta. Then once you've wrote out it in de Moivre's theorem, you can write a plus bi, the other side, in exponential form as well. Okay, remember to just pause if I'm going too fast. So in this case, a plus bi is the modulus function on the front and the argument up there. All right, so nothing new there. Just find the modulus and argument of that, put it into that form. Then what you can do is you can compare. So the front bit, the a plus bi, the modulus of a plus bi, has got to be equal to Rn. Those 2 have got to be the same. So with a simple bit of rearranging, taking the nth root, then you can work out your R value. Same with the other parts, compare the arguments. So we know that the argument of the complex number is always equal to n theta. So we can write that down, making sure we're aware it's equal to n theta, so therefore it's going to go to n lots of 2 pi, which is what this says. Add multiples of 2 pi to the n theta till you get n solutions. So starting with your first answer, which is always just the argument, which is the initial value, just keep adding 2 pi till you have however many solutions as the power is. Once you've done that, you've done all the hard work. You need to divide each of the n thetas by n, okay, to make sure you've got the correct answer. And then once you've done that, then you can write out all your solutions in the form r equal to I theta and change to a plus bi if it's required. You don't always have to do that, so just be aware, don't waste extra time in that exam if it only wants it in this form. Okay, right, pause there if you need more time to copy it down. Right, 2 other important facts. When you've got the roots of the equation z to the n equals a plus bi, the solutions to it, and you plot them on an Argand diagram, they will always form the vertices of a regular n-sided polygon. Okay, so it doesn't matter what power that is. Okay, even if it's up to 20, you would have a 20-sided polygon in there. the sum of n roots of the equation is always going to be equal to 0. So when you've got your solutions, if you add them together, it will always equal 0. Okay, a simple example of this could be if you imagine looking at when z squared equals 4, for example. If z squared equals 4, it only has two answers, 2 and minus 2. And when you add those together, you can see 2 plus minus 2 equals 0. So a very basic example, but it's always true. Okay, pause if you need to. Right, so I'd like you to just have a go on the exercises on 1C. All right, have a go at all those exercises before we move on. Okay, very quickly then. Given that z to the power 4 equals 1, find the possible values of z. All right, so a bit of a recap of the previous bit. And you should have got 1. You should have got minus 1. Those two are obvious. But the other ones that you may miss would be I and minus I. Okay, knowing that there's z to the 4 means you're definitely going to get 4 solutions. Right, we're going to write these roots in exponential form. So in this case, we're going to write each of them in e to the I form. So we know that the R value is going to be 1, and to get to 1, the argument is going to be 0. All right, so pretty obvious, the first one. Second one, we know that the argument, the modulus is going to be 1, but the argument to take you from the real line up to the imaginary line, you have to turn 90 degrees, which is where the pi over 2 comes from. To get to minus 1, it's going to be modulus 1, but to get from positive 1 over here all the way around to negative 1 over here, you'd have to turn 180 degrees, which is why we've got pi in there. And then finally, to get to minus I, we'd need to turn 270, which is where the 3 pi over 2 comes from. Now I can rewrite these using just equivalent powers. That's what I'm going to do. So it seems a bit strange, but you'll see why in a second. So I can write 0 as 0 pi over 4. I can write pi over 2 as 2 pi over 4. I can write pi as 4 pi over 4. And I can write 3 pi as 6 pi over 4. And the reason why I've done that is because then you can clearly see what's happening with each of these stages. You're going to get from one to the other, you're multiplying by a certain value. Each of those, if I want the third root or the third solution to this equation, I can just write 3 lots of 2 pi I over 4. I can just write it like that. Okay, and that should work for each of those values. Okay, so if you just grab your notebooks. The roots of the equation z to the power n equals 1. So it's important we notice in that it's equal to 1. Unlike the previous bits of work we did a little while ago, these ones seem more simple because they're only equal to the number 1. And they're called the roots of unity. The square root, the roots are equal to 1 are always called the roots of unity. Roots of unity, often, and we're certainly going to do it, is replaced with the Greek letter omega, although it's not a general rule. It is a fact that sometimes we can rewrite it. And I like to do it just because it differentiates then whether it's a root of unity or some of the previous work we were just doing. So we know from what we just saw that if we've got the roots of root z to the power of n equals 1, then each of the solutions will fall into this formula just here. If I want the first answer, in other words, when k equals 0, then I'm going to get 0 I over n, or just 0 I, and that's where the answer 1 comes from for the first solution. I can then put 1 into it, so I get 2 pi over n, 2 into it, 4 pi over n, and so on. I stop when I get to the number before whichever one I'm working at. So if it's z to the power 7, for example, I will stop at number 6. I will still have 7 solutions because you're including the 0. That formula, as it says there, is given to you in the formula book. So you will not expected to learn this formula, but you will be expected to be able to use it. Okay, so let's see why. What sort of important facts come from it. Now z naught is always, omega naught is always equal to 1. Your first root is always equal to 1. There's nothing wrong with saying z naught, by the way. The first root is always equal to 1. Once you've got that one, your second solution is going to be 2 pi n. It means the argument has gone up by 2 pi over n. That's the only difference between the two solutions. The r values, the modulus, is always equal to 1, so it's still got a distance of 1. The only thing that's changed is the fact that the argument has changed by 2 pi over n. That's how you get to the second root. In fact, if I want to get to any of the other roots, I just keep rotating from whatever 2 pi over n is. And that's what it's saying there. Generally speaking, if I want to get to the next root, I just keep rotating round, as you can see from the diagram, by 2 pi over n. Got a fifth solution there, and the sixth solution, and then back to where I started. Okay, none of that should be a major surprise because you've got that polygon that we talked about before. Okay, which is a solution to, in this case, z to the power 6. Okay, you can see that there. So we get our nice, in this case, a regular hexagon. But it's important to notice that the argument for any complex number, any root of unity in this case, is always going to be some amount of 2 pi over n. So if I want this third solution here, first solution, second solution, third solution, the third root, what's the argument of that? Well, I have to turn 2 lots of n, 2 pi over n, so 2 lots of it. Okay, some other important facts. The W1, so that will be the second root in this case, when k equals 1, so 2 pi I over n, is the complex conjugate of W5. And regardless of whether it's n is odd or even, this is always true. Okay, the second solution is always going to be the same as that one. So, more generally speaking, it's important to be aware of that fact, that if I've got W1, it is a complex conjugate of the one before the end. Okay, one before you get back to number 1. And notice that that's true for W2 and omega 4, omega 2 and omega 4, same there. So more generally speaking, you can get this fact. Now in this case, just have a quick look at omega 3, that fourth solution. Okay, that fourth solution out of a possible 6, if it was z to the power 6, notice that number 3 is saying that omega 3 is equal to omega 3. And the reason for that is because it's real. There's no imaginary parts, so those two would be exactly the same. Omega 3 would be exactly the same as its complex conjugate because there is no imaginary parts. If it was z to the 7, you'd have 2 solutions either side. You would not have negative 1 as one of these solutions. Okay, right, so if I've got the omega 3 equals that, then I can do this fact. Check you're happy. All I'm doing is taking the k outside. So I've wrote it like that. And the reason why I can do that is now I can use my laws of indices and take that k up as a power. And why would I do that? Because I want to know it's an important fact. I know that e to the 2 pi I over n is exactly the same as the first, not the first one, because that's number 1, but the second root when k equals 1. Now in this case omega 1. So if I know that's omega 1, then what I can say is that fact just there. That if I've got, let's say, the fourth root in there, so omega 3 in that case, is going to be equal to omega 1 cubed. They're exactly the same. That's going to help when we come to solving some equations and I want to be able to replace and maybe write everything in terms of omega 1, for example. Okay, some other important stuff to notice, that if I wrote out all the solutions, so there we go. This is for a general formula, for a general power n. I know that it keeps going like this up to the final answer, which is going to be e to the n minus 1 lots of 2 pi over n. Okay, once I've gone past that, I'm back to number 1, I'll rotate around again. I've noticed that I can pull out a 2 pi I over n from each of these. So just check you're happy with my reasoning here. 4 pi I over n is the same as that plus that. 6 pi over n is the same as 2 pi n plus 4 lots of it. That is the same as 2 plus 6, and so on, right down to the end facts just there. Now, the reason why I've done that is because now what I can do, using the laws of indices, I know that if I add powers, I can pull those parts out. And the reason why I've done it is just to show you that actually you're dealing with a geometric series here. You're multiplying by the same thing on every single time. So I can say that my A value is going to equal 1 and my R value is going to equal 2 pi I over n. So that is what I can get from that fact, that if you wrote down the roots of unity, then you're writing down a geometric sequence. Right, why is that important? Well, if I look at the summation of all the roots, I add up all those possible roots. So the sum of the first n roots, which of course will be all of them, because it only goes up to n. If I add up the first n roots, then I'm going to get a minus r to the power n all over 1 minus r. So I've got that answer just there. And once I've done that, what I can do is just do a bit of simplifying. So I can see I can simplify this. This to the power n is the same as times by n, so that's why that n's disappeared there. I've got one lot of it, which of course is going to disappear in a second. But we know that e to the 2 pi I equals 1. We know that because you're looking at, if you think about what this number actually is, it's got an argument of 1. Sorry, it's got a modulus of 1, and it's got an argument of 2 pi. So if you imagine you're stood at number 1 and you rotate 2 pi, you're back to where you started. So e to the 2 pi I equaling 1 is an important fact. Okay? And once we've got that fact and we remember that fact, it makes these a little bit easier. Because what we're looking at here is we're writing this as 1 lot of 1 minus 1. That is just the number 1. Why is that important? Because then the top bit goes to 0. 1 minus 1 is 0. So therefore, what have we proved there? That the sum of all of the roots of unity, doesn't matter what they are, when you add them together, always equals 0. So we saw a nice example of that earlier, but now we've managed to prove it mathematically using sequences and series. Okay, right, so let's have a look at an example. So grab that down in your notebook. By all means, pause, have a go yourselves. If you don't want to, by all means, just follow this first one through. So show that the non-real cube roots of unity satisfy this equation. So we'll just have a look at that in a second. The real number a satisfies this thing here, where the omegas are the roots. Okay, so omega squared are the different roots of the unity. Just talking about there, it doesn't matter which root it is, it could be any of them. Okay, z squared, so looking at just 2. Find the possible values of a. Right, so let's go through and just see how we do that. So pause if you need to. Okay, so the cube roots of unity are the roots of the equation z cubed equaling 1. Okay, so we're looking at the cube roots of unity. Where did you get that from? It's talking about it just there. The cube roots of unity. So because I'm picking that out, I know that means z cubed equals 3. Okay, so I'm looking for those key words. Right, once I know that fact, I don't need to keep doing loads of work. I can get the formulas from the formula book and just use it straight away. So the formula from the formula book says this is how you find your cube roots of unity. In this case, we're dealing with Z3, so that stops at number 2. Don't forget, 3 answers, 1, 2, 3. So I'm going to ignore all of that part, and my answer will be K0 equals 1, K1 equals 1 lot of that, and K2 equals 2 lots of that. So I'll get 1, there's K, there's putting number 1 into it, and there's putting number 2. Those are the cube roots of unity. Right. Why does that help me? Because now what I can do is I can show it satisfies this equation. The real solution, the non-real cube roots are those two. This one is number 1. Notice that doesn't get you 0. Okay, in this case. That's why it's important not to think, oh, it doesn't work. 1 squared plus 1 is 3. Doesn't make any sense. But they're saying, look, the non-real cube roots of unity satisfy this equation. So just the non-real ones. The real one does work for it. So let's just check. We've only got 2 numbers to check. Let's just put them in there and just verify it actually works. So for example, the first non-real root. If I put that in, it equals that. I can substitute that into here. So I've got that squared minus that plus 1. Right, a little bit of working out. I'm going to get a quarter. I'm going to get that bit, which is that times that. I'm going to get minus a third, 3/4, which is that. And lo and behold, when we've worked this out, plus an extra 1 equals 0 as required. So I've put it in and I've checked it. It definitely works in that equation. What about the other non-real roots? So that's 4 pi. So I'll do the same bit of work again. I write it as a complex number, right? No different. In fact, it's interesting to notice it's the complex conjugate of it, like we discussed before. So therefore, because it's a complex conjugate, it should really be the same answer. But let's just confirm it. So I've got squared that. Notice there's a minus here rather than a plus before. But that doesn't matter because you get the plus in this bit now. So a quarter plus that bit minus that. Those all equal minus 1. But plus 1 makes that to 0, and that cancel out. So 0 as required. So I've done part A. I've found the non-real cube roots, which is those 2, and I've checked they satisfy that equation. So that first bit is ticked off. I'm done. Okay, pause if you need to. Right, so look at part B then, see what this bit's on about. So the real number A satisfies this equation. So I've got this beastly equation here, very similar fractions except for changes in signs, where omega is one of the non-real roots of unity. So one of those 2 previous answers. Not that I'll probably need them. Right, so what I've done is I'm just simplifying it. I want to be able to compare these. I want to solve it as a bit of algebra. I can't really think what else to do, so I'm just going to multiply these 2 together. So add these 2 fractions, sorry, by multiplying the denominators and so on. So I've got down to this. Right, let's see what this does then. Well, if I just do a little bit of neatening up, and notice the top actually works out quite nicely, doesn't it? That root cancels with that root squared cancels with that root squared, so I end up with just 2a on the top. You might be thinking now, oh, can't you do a bit of work with the compared tops and bottoms? Potentially, but that's not going to help, right, in this case. So I've got that. Notice I've just expanded that bottom part, and that's cancelled out. So I've got the a omega cancel with that minus a omega. That one's going to cancel with that, and so on. And I end up with this. Okay. Yes, I have noticed that I've got 2 of the omega 3s. So those 2 are great. But why does that help me? Right, so what can I do with it then? Well, I know that omega to the power 3, any root cubed, is going to equal that. Why does that help me? Well, actually, if you think about it, because it's a cube root, if you're cubing it, they will cancel each other out and just get you back to where you started, which in this case will be 1. I'm just proving it to you. So e to the 2i over 3, or e to the 4i over 3, it doesn't really matter which one you choose, goes to e to the 2 pi I, which is back to 1, as we discussed before. There's the real number 1. If you rotate 2 pi, you're going to get back round to where you started. So back round to 1. If you don't know that fact, write it down, learn it. Okay, it's a rather magical result, and just worth pointing out. It's a nice result of e to the 2 pi I always equals to 1. And we've got omega to the 4 equals omega cubed times omega. So if I'm dealing with omega to the 4, which is this one just here, I can write that out and say, well, actually, that's the same as omega cubed times by omega. It's the same as the root to the power 3 times by the root. Now, I've just showed that the root to the power 3 is equal to 1. So really, omega to the 4 is just the same as omega. They're the same thing. Right, why does that help me? Because that means I can simplify this part a bit more here. I can definitely rewrite it as a squared, can't do anything with that. That can't do anything with that. These two are just number 1, so that's fine. And this one I can write as the same as omega. Right. What else can I do? Well, maybe a little bit of rearranging. So yes, I can put those two together. And maybe I've got to use something to do with the first equation. There was no point in the examiner giving me that first equation up here if I'm not going to use it. And maybe you should be looking and thinking, oh, actually, there's something similar with it here. It's not quite the same, is it, though? Because I've got minuses on there. It doesn't stop me doing some work. All right. If I use that fact and say, well, I know that's true for either of the non-real roots, that omega squared plus omega plus 1 equals 0, where that's either of the first two solutions. Why does that help me? Well, if I can somehow rearrange that, there we go, I know that minus omega squared minus omega equals 1. Oh, look, that's what that bit is. That's what that bit is. So really, this comes down to this fact just here. And if I know that, I can then do some rearranging. So 4a equals a squared plus 3. Just to rearrange it slightly more. Oh, look, a nice quadratic comes out at the end. So therefore, my two solutions are a equals 1 and a equals 3. Okay, get into that fact at the end. Okay, just one last bit of work before I give you some exercises to do. So sometimes what they do with these as well is, as you know, these are the roots, these are the solutions. And as you've seen in normal maths, is often when they have roots and solutions of equations, they often link those to factors as well. So in this case, because we know that these are our solutions, these are our roots, can you then write down the factors? And it's no different just because it's complex numbers. If you know that these are your roots, these are your solutions, then we could definitely write z to the power 4 as these 4 factors. Okay, z minus I, z plus 1, z plus I. Now these two are already real factors. Yes, a z number is a complex number, but these two are their real factors. These two are non-real factors because they've got the minus I and the plus I in there. But I can write them in terms of those bits just there. Noticing that you're rearranging and making it equal to 0. Yes, those might be the roots of the equation, but it has to equal 0 for you to be able to do any sort of factorising. So that's where that part's come from. Z to the 4 minus 1 has these if you factorise it. That's real, but these two aren't. So if I want 3 real factors, I leave those two alone, and I just multiply these two out. And because they're the complex conjugate of each other, then what's going to happen, you're going to get those two. Yes, it's not quite as easy as just being a complex conjugate. You could argue that these two z's are not quite, if you expanded them, they wouldn't necessarily be the exact complex conjugate. Yes, you're right. But the fact is, because you're multiplying them through, those bits will cancel the same way as if they were complex conjugates. So we've got z squared, we've got plus z, we've got minus z, and we've got minus, it's there, isn't it? Minus I squared, which was where you get plus 1 from. So well done if you managed to get down to that equation just there. Okay, that's where it's been factorised. Right, what I'd like to do is just have a go at those two big exercises. Take your time with them, don't rush them, and then go from there. Okay, we're going to look at 2 more examples. Multiplication of roots is equivalent to a rotation about the origin. And this is more about how they use roots of unity in geometrical situations. Okay, so grab your notebook, get that first bit down. The multiplication of roots of unity is equivalent to the rotation about the origin. Now we did allude to this earlier on when we talked about it being a rotation of 2 pi over n. Let's see how we can actually use it to help us solve these types of equations. So the point z is a rotation of the point a plus bi, or is rotated by that angle. So the point z, which we don't know, is a rotation of the point a plus bi by the angle 2 pi over n. So where would it go to? Well, I know if that's 2 pi over n, I don't know how big that is, I'm just sort of doing it as a rough guess, then I know that it's going to go from there to there. Okay, it's rotated around. So if I want to find out what z is, I can multiply it by 2 pi I over n. If I multiply it by that root just there, that solution, it's not going to change its magnitude because it's still only got a modulus of 1. And this bit, as I know, is a rotation of 2 pi over n, which is what we looked at before. So if I want to find out what that value is, all I need to do is multiply it by this part just here, and that would get me my new number. Okay, right, so let's look at that as an example. The origin of the point 4 plus I are 2 vertices of an equilateral triangle. So I could just plot both of those. So I've got my origin, there we go, that's one corner of it. I've got 4 plus I, that's another corner. Why is it important to know it's an equilateral triangle? And if you see those words coming up with these types of questions, you should be thinking, oh, that's to do with roots of unity because it's to do with a regular polygon. In this case, a regular 3-sided polygon. So the roots of unity can be used to find that third vertex. It's going to be up here somewhere. There's 2 of them. There's the third one. There's my regular polygon. Right, what's also special about an equilateral triangle? I know this angle here is going to be 60 degrees. So I know that for a fact. Be very careful not to think, oh, equilateral triangle is 3, so therefore it's going to be z to the power 3, okay, because you'll make mistakes when you divide in by the wrong number there. In this case, we need to be aware that because it's an equilateral triangle, it actually forms part of the full bit around the outside will be a full hexagon, which is where the 6 comes from. But just be aware of what angle they're talking about. So this is going to be 2 pi over 6 for an equilateral triangle. Right, so why does that help me? Well, if I know that that's 4 plus I, how do I rotate round to there? I need to multiply by e to the power 2 pi over 6 I, which is where that comes from. Now, if I multiply it by that root of unity just there, then it should take me round to the next bit. The first thing I'm going to do is just change that into that form, because then I can multiply them nicely. So I get cos to the 2 pi over 6 plus I to the sine 2 pi over 6, and I'm going to multiply it by 4 plus I. So there we go, that's simplified that bit out. So the third vertex is going to be e to the 2 pi over 6 times by 4 plus I. So what do I get? That times that, you can see how to expand it. Simplify that out, gets us this number just here. Okay, 4 minus 3 root 3 over 2 plus I lots of 1 plus 4 root 3 over 2. That's the exact answer, but it's going to be roughly up there. If you type it in your calculator, you'll see what the decimals are. Okay, right. You clever people out there that thought, actually, how did you know it's going to be up there? It doesn't have to be. What I'd like you to do is find the other possible third vertex, because you're quite right. It didn't have to be up there from the first bit. So I'm going to pause, give you an opportunity to think what I'm on about, and give you an opportunity to see if you can work it out. Okay, so if you didn't spot it, the other answer could have possibly been down there. Okay, in which case you are still multiplying by 2 pi over 6. So you've got 2 choices. You can either multiply by minus 2 pi over 6, because you're going back on yourself, or multiply by 10 pi over 6, which is 2 pi minus 2 pi over 6. And that would get you this third answer. It's how you'd rotate backwards. But apart from that, it's all going to be the same answer. Okay, the same way of doing it. So you're thinking about what the root of unity of minus 2 pi over 6 is going to be, which gets you a very similar answer to the previous one, just with the minus I root 3 over 2. And then from there, you're multiplying it. So there we go. Gets you that answer almost identical to the previous one, but this time you're going across there and down there. Okay. And again, you could check those 2 numbers out on your calculator. It should look roughly right on your Argand diagram. Right, some geometrical work to do on 1F. So going to have a look at those different sort of questions to do with geometry and using roots of unity to help you with geometry. Right, we're going to look at two questions at the end. These are quite tough. And this is a sort of top end of the sort of roots of unity solving equations that you might have to face. So I'm going to give you two similar examples, similar questions, but just two different ways of solving them as well. So it depends on which ones you prefer. So what makes this more difficult is the fact that you have got 2 to the power 5s multiplied together. It's not just like a nice easy z to the power 5 equals a complex number. Even z minus 1 to the power 5 equals a complex number is okay. It's when you've got two things, both to the power 5, makes it more tricky. Okay, right, so let's have a look why it makes it more tricky. You can't find the fifth root. If you try to find the fifth root, then what would happen straight away is you'd have z minus 1 equals z, and that's just not possible, because if you try to rearrange it, you get minus 1 equals 0. So something's going clearly a bit weird to start with straight away. We need to find a different way of solving it. And that's what you did before. You took the fifth root and it was all okay. This time it's not working. So what can we do differently? Well, what I can do differently is this, and it seems a bit odd, but I can write z to the power 5 on that side with a number 1 on the front. So it's the same question, okay? Z minus 1 to the power 5 equals 1 plus z to the power 5. All I've done is chuck this number 1 in. Now, why have I done that? And the reason why I've done it is because number 1 can be replaced with a root of unity. So really, number 1 I know is equal to some amount of 2 pi I. It's equal to 2 pi I times by k. We know that because if I had, forget the k for a minute, e to the 2 pi I, we know that equals 1. Now, if you had 2 lots of it or 3 lots of it, it's still going to be the same because it will be e to the 2 pi I to the power k. So that is just the same as the number 1. So what I'm going to do is I'm just going to substitute that in. This is still the same question because this is still the number 1. Right, why does that help me? Because now if I try finding the fifth root, unlike before where I didn't have something in front of it, it does now work. Z minus 1 equals whatever this is, it's going to be a complex number, times by Z. It just can't equal 1. Right, that's important. That bit there can't equal 1 because then you're back into this same situation. But it can equal other complex numbers. Right, and that's exactly what I just said there. So you can't have k equaling 0 in this case, and you only get 4 answers. Now that might seem a bit weird because it contradicts what I said before, with z to the power 5 should be 5 answers. But just think about this question here expanded. If I expanded this bracket, the very first term would be z to the power 5. I would then get some z to the 4, z to the 3, z to the 2s, but the first term would be z to the power 5. Now, if you wrote that out, z to the power 5 plus all the other bits, then the first thing you can do is notice that you could take away z to the power 5 off both sides. And so what you actually end up with is z to the power 4 equals 0. Although these are both to the power 5s, as you can see here, actually what you're dealing with if you expanded this side and cancelled out the 5s is actually a z to the power 4, which is why you have only 4 possible answers, not 5. Right, so let's see why this helps us though. Now I've got that. All right, I've got the k equals 1, 2, 3, and 4, can't equal 0. What can I do then is I can rearrange this equation. I can rearrange it, I can bring this over this side, and I can take the 1 over there. Starting to get towards a sort of roots of unity type question because I can see it's equaling 1. And so therefore z on its own is going to equal this just here. Okay, so I can see I'm dividing by 1 minus that. Why does that help me? Because then I can multiply by its complex conjugate. All right, we talked about this in the previous complex numbers part, noticing that if I want to cancel any imaginary parts off the denominator, then I can multiply by the negative version of it. So I get this. It doesn't matter, it's not quite the same, it doesn't matter, that's 2 pi. This is pi, it will still work out. So I've got to that. Why does that help me? Because then what I get is this answer just here. I've noticed that that is the same as that. These two, when they multiply, why did I choose -1 of it? It's because the 2 and the -1 there will get back to just a single one of them. They don't cancel out, they get to a single one. This part down here, with this being a negative and this being the positive version, not the negative on the front, the actual power, this being negative, this being positive, we've seen that pattern before. We've seen that pattern before when we came to doing it with the de Moivre's theorem earlier on. So I know that that is equal to that. Why does that help me? Because now I can replace, I can see it's pretty much identical to this, but with a theta value equaling k pi over 5. So I can replace that bottom bit for that, and the top bit I've just expanded into cos and sine form. So there we go. Okay, so I've expanded it to cos and sine form, and then I can separate into real and imaginary answers to get that answer there. Okay, not straightforward. As I said before, with some of these tough questions, the examiner will be holding your hand quite a bit, making sure that you've got plenty of hints and tips, or it could be that it's just part of another question that you just need to spot some errors. So just that understanding. But you're seeing these same tips, these same tricks coming out every single time, okay, using these sorts of facts. Not quite finished though. Let's just have a look how we can simplify it slightly more, or how you might need to simplify it slightly more. We know that sine to the minus is the same as minus sine, and we know that cos with a minus is exactly the same as cos because of the reflection that we talked about before. This fact here you've used a lot now. Right, so why does that help me? It just means I can simplify these two parts out on the top. But also noticing that actually I've got cos over sine and sine over sine. So these two can cancel out quite nicely. So these two can cancel. The i's can cancel, leave me at half there. The cos and the sine can cancel, but I'm stuck with that I just there. But it does lead down to a nicer fact. What can I do with that I part? Well, to get that to the numerator, I could just multiply top and bottom by I. If I do that, I get I over I squared, but the minuses will cancel each other out and leave me with I over 2. So the real part will be a half, and the imaginary part will be a half cot k pi over 5. Well done if you managed to follow all that through. What we're going to do is we're going to look at another similar example, but with a different power. So there's your final answer, where the k value could equal 1, 2, 3, or 4. So you could write out the solutions if you needed to. Okay, get down what you need. Pause if you need to. Right, so it looks like it's almost the same. Z plus 1 to the power 4 equals Z to the 4. So write it down, pause, have a play with it yourself. You might want to just see if you can follow some of the previous steps. I'm going to show you a slightly different way of doing it. Right, so see how far you would have got. So first write down that bit. So putting in that number 1. Whenever you've got this situation where you can't just do the 4th root, it doesn't work, you should be thinking, oh, well, it's got to be one of these tricks. Put the number 1 in. So if we put the number 1 in, then I'm putting that equaling 1. Not sure why I changed the 2 in a different place, doesn't make any difference. So there we go. I put that in there. Why does that help me? Because now I can find the fourth root. Okay, so I find the 4th root. There we go. And now that I've found the 4th root, I can rearrange. We know how you can't equal 0 because that's going to get you back to z plus 1 equals z, which can't work. So, and same as we said before, if you expand this, you will get z to the power 4 to start with, which will cancel, leaving you actually a cubic equation. Okay, so we know that. Why does that help me? Because now I can rearrange this to get down to this fact. And that's all quite similar to before and nothing majorly different. This bit is the bit that's quite tough. So what we're going to do is we're going to look at solving this a slightly different way. See if you prefer this. You don't need to learn both. All right, either of them is preferable. But this option is to change that value straight away. So we're changing it using the fact that we know that z, the complex conjugate, is going to equal that. So therefore the complex conjugate is e to the minus I theta. That fact there I've shown you a few times, and we know that e to the I theta is the complex conjugate of e to the minus I theta. So knowing that they're the complex conjugate of each other means what I can do is I can multiply this by its complex conjugate just there. Okay, so just check you're happy. I'm just multiplying by its complex conjugate, so I've just changed that to a minus. Everything else stays exactly the same. Now the only difference between that and the previous one is that we brought in some multiplications before that. So what have we got? Well, we've multiplied those through. Once I've done that, I can simplify the bottom. So these two are cancelling, multiplying by together. These two. Oh, what I've noticed is these two though are it's quite nice. It's going to get me 1, so that's going to get me that plus 1. The top I can't do much with, so I end up with this fact just here. Noticing that the bottom has ended up being exactly the same as the previous one, but in this time I've got a minus and a minus, so really it's that plus that with a minus taken out. Okay, the powers opposite again, so I'm using this fact just here. I've rearranged it and shown you where the minus comes from. So yes, we know that, but if I put a minus in front of everything, that is what I've got just there. Okay, these two the other way around, but it doesn't really matter. It still works out fine. So really, this bottom bit is going to be 2 minus 2 cos theta, where the theta value is the k2 pi over 4. Okay, so I've got that. Notice that I've opted for the minus version. And the reason why I've opted for the minus version of theta, it's exactly the same. You know that cos of minus is the exact same as cos of plus. So it doesn't matter if you didn't do it. But I've just put minus because I know I can cancel with this, which was that bit expanded. Okay. So I've changed it back now. So just because I've done the same with that one. So those two are changed. Notice that I put this in with a minus 1. If you didn't change it, these two would still be minuses. That's fine, doesn't make any difference, because what I've noticed is that these two hopefully will do some cancelling out. Once I've got that, now I can separate the real and imaginary. So there's the real parts, there's the imaginary parts. So these two above each other would get me minus a half. These two would get me this part just here. Okay, why is that helpful? Well, that is going to be cancelling with that, which leaves you that minus a half. These two, I can do a double angle formulas. Just notice what I did there. I took the 2 outside the bracket. Okay, so I took the 2 outside the bracket, and if I've done that, then I can rewrite this top double angle like that, and I can rewrite the bottom double angle, cos of 2 theta, like that. What does that get me? It gets me 2 sine pi k pi over 4 cos k pi over 4 with a 2 being brought to the front. This one, same idea with this number here, bringing that 2 outside, which it always is, and inside you've got 1 minus 2 lots of sine k pi over 4, take away 2. So we've got that. Why does that help? Now, if I expand this bottom part now, I can see I've got 2 minus the 2, so they're going to cancel out. I'm also going to get 2 times 2 is minus 4. 2 times minus 2 is minus 4. Oh look, sine and sine will cancel, and I've got cos over sine, which actually, cos over sine, yep, the I is still there, but the 2 and the 4 cancel, the minus has gone to the front, so therefore I can write it now as a cot. So my end answer is minus a half cot pi over 4. You can see it's a very similar answer to the previous one with the cot being brought in. Don't forget you've got the k values of 1, 2 and 3 in there because there's only 3 solutions. So it's an alternative way of doing the previous one, but you can pick either bringing in the causes and the sines early and using your derivative skills there, or bringing them later and manipulating it with an exponential form. You can choose. Okay, right. Just be very aware that those questions you just did, as I said before, I'm reiterating the same fact, you would not be just given that as an exam question and expect to be able to do all this manipulation. You will be given some hints on that. You may have to show part of it, or they'll give you a full solution with some errors or something like that. Okay, right.